Hello and welcome to my NBody demo. Here, as you can see, I have an NBody simulation where I'm simulating planetary physics between N bodies in a system. This was done as part of my computer graphics tutorial, where I spent a lot of time working on the rendering pipeline and writing my own game engine in a sense. Some interesting things about the simulation. It utilizes something known as the BH tree or the Barnes-Hut tree algorithm in order to cut down on a lot of the computation expenses. I'll show that later in the video. To actually calculate the gravity, I just use standard gravity formula where the force equals the gravity constant times mass 1 times mass 2 divided by the distance between the two bodies, and then use some vector math to translate that into a force vector that I can then apply to the velocity of each of the planets. And what you're seeing here, what you're about to see on the screen, is a simulated planetary explosion where I have a lot of these planets coming in at a strong velocity, and we can emulate kind of like an explosion in a system, which is pretty cool. I will also note that this is a collisionless system, so there are no collisions. However, the visuals I still get from it are pretty interesting and a lot of fun. Some other the math involved in this includes the calculating the original tangential velocities of the bodies in a normal simulation. The one you're seeing here is an explosion, so this doesn't apply to this. But for something like that, I just simply take the cross product of the up vector of each planet with the vector from the origin to the planet itself to get a perpendicular vector to the origin, to try and get kind of like an elliptic velocity in a sense, so that way we can have the planets elliptically orbit around the origin or wherever the highest body of mass is. Okay, so for an N-body simulation, this is how we can kind of start. And first we can think about it as having two bodies, right? If you have two planets, it's fairly easy to calculate the force of planet 1 and acts on planet 2. But then, if we throw in a third body here, now it's not just planet 1, planet 2, you have to now account for planet 1 affecting planet 2 and 3, planet 3 being affected by planet 1 and planet 2, and then planet 2 being affected by planet 1, 3, and affecting both 1 and 3. As this grows, you can quickly see how this becomes a very hard problem. So this quickly goes to n squared complexity, which is not very feasible for very large n-body problems. As n grows, this becomes very computationally expensive. So there's an optimization or a different algorithm that we can use known as a BH tree or a Barnes-Hut tree to kind of speed this up. And what this tree and what this algorithm basically does is it breaks up our nodes from up here, our planets, into first an octree or a quadtree. So for this example, I'm going to be showing this in a 2D plane, just for some simplicity, but this does translate directly to a 3D model. Except instead of a quadtree, you're going to use an octree. So for the 2D model, first we're going to have a planet. This is going to be our origin or whatever we want to do, or whatever we want to call it. And then based on where our next few planets lie, they'll be put into a tree structure. So this might be planet 1 up here. This might be planet 2, 3, 4, 5. And how you would decide this is your first planet would be like here on the plane. And then say planet 2 is here. Planet 3 is here. Planet 4 is here. And planet 5 is here. Then what happens if you get planet 6? Well, for planet 6, you would have something like, I don't know, say planet 6 is right here. Well, then you treat this as its own separate plane. Planet 6 would then go up here for 2. So you have planet 7 is down here. And you would just populate this just like you would any standard quad tree, breaking these up into quadrants. Now, where the optimization comes into place is planet 7 right here is still being affected by each of these other planets that we can see here. However, planet 7 may only barely be being affected by, say, planet 2 and planet 6 up here because it's just so far away. Using this, we can optimize our algorithm substantially. So say when we go to calculate the amount of gravity being acted upon for planet 7 here, instead of calculating both planet 6 and planet 2, we can just take an average of both of these and just end the calculation right here. Where you see this get extremely beneficial is when these trees get larger and larger and larger. And you have some distance, right? Some distance here that is your cutoff. If something's more than this far away, just take the average of everything that falls beneath it in the quad tree. Allowing you to save all the calculations that would happen within this section of the quad tree or with any node that lies outside of D, this distance here. With this, as you may be able to already see, you're going to have to reconstruct the tree every so often. The frequency of this is up to the user itself, but due to the nature of this, all of these bodies are going to move. 7 might then be over here after some time, and now it's not lying on the same plane in the quad tree, so the distances aren't the same. So you're going to have to recalculate your quad tree very frequently, which is going to be n, right? Because you have to go through n nodes to calculate and build a new quad tree. Then, along with this, you're going to have to traverse this tree. And the traversal of this tree is actually just log n, which is much faster than an n squared algorithm. And in this simulation I have here today, I use this, however, with an octree to represent it in a 3D plane and speed up my algorithm exponentially so I can have hundreds and hundreds of nodes without having to worry about this n squared complexity.